Hello everyone! In this video, we will continue to examine topic 7.2 nuclear reactions, and in particular continue to unpack the relationship between mass and energy. In the previous video, we introduced this general idea of mass-energy equivalence, that energy and mass are equivalent. This is usually captured in the famous equation E equals mc squared. More precisely, E equals m naught c squared for the rest mass, for objects that are not moving. Now, this had several interpretations. The IB and useful one, in which we consider energy being converted into mass, or vice versa. But then the more correct version, in which we consider the inertial properties of a system depend on its total energy content. In other words, mass is a measure of the total energy content. If the energy content of the system increases for any reason, the inertial properties of that system also increase. But in some senses, this begs the question that we initially asked, which was, why is the inertial mass of a system equal to its gravitational mass? You notice that phrasing that I just used only mentions the inertial mass and doesn't comment on sort of the gravitational mass or the gravitational properties of the system. And in part, that's because special relativity alone can't quite handle anything accelerating. But the incredible insight that Einstein had in moving to the general theory of relativity, which ultimately is a theory of gravity, is that it can treat this idea, this relationship, the relationship between the inertial mass and the gravitational mass as being equal, as effectively a postulate, and then see where it goes. So the same relationship that the special theory of relativity has to those first two postulates back here, that the speed of light is constant in a vacuum in all inertial reference frames, that the laws of physics are the same in all inertial reference frames. Well, if you take the special theory of relativity and what is known as the principle of equivalence, which is a formal statement of the fact that the inertial mass and the gravitational mass are indistinguishable, you get the general theory of relativity. The principle of equivalence, which is in many ways just a rephrasing of this idea, is that there is no physically discernible difference between an object accelerating and one in a gravitational field. That is, the things that cause objects to move as if they are under the presence of gravity looks exactly the same as the things that cause an object to accelerate, and the effect on the object is the same. So if we take a look at sort of how that works, imagine, the classic example is to imagine that you're in an elevator being pulled up with some Ft tension, right? You are accelerating upwards, but what do you feel? Well, inside the elevator, you don't know necessarily that that elevator is pulling up on you. You feel a normal force on your feet, which is exactly the same thing that you would feel if you were standing on the surface of the Earth inside the elevator and under the influence of the gravitational field of the Earth. And the idea is that not only are these things sort of seem the same, or epistemically, sort of if you're in the box, you can't tell which is which. But the idea is that the underlying explanation of what is going on must be identical. And the reconceptualization of exactly how gravity works is pretty thoroughgoing, and so there's a lot to know, but I'm going to try to hit the main qualitative points in what I'm about to say. It turns out that the fundamental explanation for why this is that mass, and therefore energy, curves space-time. And then all particles, including light, follow straight lines in curved space. So, our initial explanation for why a moon or something like that might orbit a planet was that the planet pulls on the moon, with an extra force. Now we reconceptualize what's going on. We have a completely different explanation. There's no pull. Instead, what happens is that that central planet is curving the space-time around it. Okay, it bends the very fabric of what it is to move in space around it. And as a result, an object that sort of drifts in its vicinity, okay, will follow a straight line in that curved space. Okay, and if it follows a straight line in that curved space all the way around, well, now you have an orbit. But there's no pull. That object is not being pulled. That object is simply moving in a straight line in a curved space. And that's exactly the same as if the object were curving in a straight space. So it is identical to what it would be for that object to accelerate centripetally, something like a car going around a track in a circle. It experiences exactly the same kind of motion through space. One is a straight line in curved space, the other is a curved line in straight space, and the effect is the same. And this is a very, very concrete prediction, which is that, as it turns out, for this conceptualization of gravity, things that do not have mass are still affected by this, including light. Massive objects, including stars, bend light in this way. Light obeys gravity. We don't normally notice this because light is moving so fast, and this bending is so weak. But this is a verifiable prediction of the general theory of relativity, and one of its strongest supporting factors. It was the single strongest piece of evidence that the general theory of relativity was correct. Now, the fundamental language of the general theory of relativity involves tensor calculus, which is way beyond the bounds of this course. Tensor calculus and differential geometry, both of which are accessible to sort of mid to high level undergraduate, if you're interested. But the field equations that came out of the general theory of relativity are interesting even though we won't use them. And this equation, the Einstein field equation, summarizes a lot of what is going on, and so it's worth just taking a look at. These symbols, that r mu nu, so capital R mu nu minus 1/2 r g mu nu, is a big long term that simply corresponds to the curvature of space-time. Okay, so this captures what is happening with space and time for that matter. So space-time has its own term, its own description in the general theory of relativity. And over here on this side of the equation, T mu nu, that's the stress energy momentum tensor. So remember that energy and mass are a measure of the same thing, that is, mass is a measure of the energy content of a system. So this is really capturing all of the stuff, and for that matter, what it's doing, if it's moving, for example. And you'll notice this is capital G. That's our friend, the gravitational constant. It hasn't gone away. That's the speed of light. So this is just a constant. And what this equation says is twofold. One is mass, energy, and momentum bend space-time. They affect the left-hand side of the equation. Not only that, but space-time and how it's structured at any particular point will end up affecting that stress-energy tensor. So not only so that corresponds to the following two sentences. If mass energy curves space-time, then that's mass energy affecting spacetime. That's this statement right here. And if particles, including light, follow straight lines in curved space, that says this term right here, which is the description of space, affect the motion and action of this term over here, that stress energy momentum tensor. And so you can see how the equation captures both of these sort of fundamental ideas. So, big picture, why is the inertial mass of a system equal to its gravitational mass? Our answer is a very long one in some ways, but it's basically the idea that, well, assume they are perfectly indistinguishable. What do you get? Well, you get this theory of gravity, okay? There's not really an answer to this why question in so much as you have sort of a reason given. Instead, it is fundamentally true, okay? That's a postulate. And the version of that postulate is the principle of equivalence. And with the principle of equivalence plus the special theory of relativity, which is still true, you can derive the general theory of relativity, which is this particular description of how the world works.